We're going to talk about implicit differentiation. So there's more to life than just functions, although for the most part we deal with functions. But there are relations that have well-defined slopes at either all or almost all of their points. So the graph that I have up there in the corner is the graph of x cubed plus y cubed minus 9xy is equal to 0. It's kind of a cool looking little curve. And pretty much at every point, this is going to have a derivative, except for whatever the value is when it goes through the origin this way, because you've got a vertical tangent there. But other than that, over here someplace, if I pick a point, go, okay, drawing the tangent line, well, the tangent line that sort of looks like that. The problem is, if you think about it for just a second, think about trying to solve that for y. You immediately are like, oh, that's going to be ugly, because you've got two different y's in there. It would not work out very nicely. In fact, I don't know any way to do it off the top of my head. So what we're going to do, instead of trying to solve it for y so that we can find dy dx that way, we're going to use what's called implicit differentiation, which is the process of treating y like it's some unknown function of x, and then differentiating both sides of the equation using the chain rule almost always. So let's take a look at this one. If we have the relation y squared is equal to x, yes, you could solve this by saying y is equal to plus or minus the square root of x, but now you've got two different functions you're having to deal with. Instead, what we can do is think of y as being a function of x. And so one of the things that some students of mine have done in the past, not everybody, is every single y that they have in a problem like this, they set it off with parentheses to remind them that it's not just a variable, it's an unknown function of x. So what we're going to do, and almost never does anyone take the time to write this, and that's okay, but we're taking the derivative with respect to x of y squared, and that's going to be equal to the derivative with respect to x of x. So because y is an unknown function of x, we have a composite function here. So to take its derivative, we're going to apply the chain rule. We'll do 2 times, we'll leave the inside part alone, raised to the first, times the derivative of the inside part, well, that's the derivative of y with respect to x, that's dy dx. Is equal to the derivative of x with respect to x is just 1. And now all we'll do is divide both sides by 2y to get dy dx by itself. Dy dx is equal to 1 over 2y. Now, this whole business of thinking of y as an unknown function of x is a little bit cumbersome to say. So what many students do is go, okay, I'm taking the derivative with respect to x. Is this variable x? No. Then I have to apply the chain rule. I have to take its derivative and then multiply times the derivative of what that is with respect to x. Over here on the right side, the variable is x, so I'm going to take the derivative just normally. Right, since the variable matches what I'm taking the derivative with respect to. All right, let's take a look at this one. Find the slope of the circle, x squared plus y squared equals 25 at the point 3, 4. All right, so again, you're probably never going to take the time to do this, but I want you to be thinking this. I'm taking the derivative with respect to x of x squared plus y squared on the left side is equal to the derivative with respect to x of 25. So the derivative with respect to x of x squared, the variable matches what I'm taking the derivative with respect to, so I'm just taking the derivative. Derivative of x squared with respect to x is 2x. Plus, here the variable does not match what I'm taking the derivative with respect to, so I have to apply the chain rule to that. So I'm going to take the derivative of the y squared using the outer part, that'll be 2y to the first, times the derivative of the inside part, which will be dy dx. Is equal to the derivative with respect to any variable of a constant like 25 is going to be 0. Then we'll solve this for dy dx. So I'll subtract the 2x and then divide both sides by 2y. And I get that dy dx is negative x over y. So the slope evaluated at the point 3, 4 is going to be negative 3/4. What the heck? Hang on a second. Okay, that's being very weird, and I don't know why. I had a picture of that. All right, well, I'll hand draw it. So x squared plus y squared is 25. Is a circle centered at the origin with a radius of 5. At the point 3, 4, which is, say, right about here, your tangent line would look like that. It looks like it ought to have a slope of about negative 3/4. All right, here, let's show that dy dx is defined at every point on the graph of 2y is equal to x squared plus sine y. Again, if you tried to isolate y, forget it. It's not going to happen because you've mixed polynomial stuff with trig stuff. That's not going to work. But we can take the derivative with respect to x on both sides. Let's see if we can do it without writing it out. The derivative with respect to x of 2y is going to be 2 times the derivative of y with respect to x, that's dy dx. Is equal to, taking the derivative with respect to x on the right side, that's going to be 2x, plus, here my variable is not x, so I have to apply the chain rule. I'm going to have cosine of y times dy dx. I want to solve this for dy dx, so I'm going to bring the cosine of y dy dx to the other side of the equation. so that we have 2 dy dx minus cosine of y dy dx is equal to 2x. Factoring out the dy dx, we have dy dx times 2 minus cosine of y is equal to 2x. So dy dx is equal to 2x over 2 minus cosine of y. Where would this be undefined? When is a rational function undefined? What's the one thing of all of math that is forbidden?
Denominator equals to 0.
Yeah, the denominator is equal to 0. Is it possible? So I'm going to write that out. Undefined if 2 minus cosine of y is equal to 0. Everywhere else it should be defined, right? Well, adding cosine, 2 equals cosine of y, is that ever going to happen? What's the maximum value of cosine? 1, which is not possible. Therefore, dy dx is what they call everywhere defined. The graph for that looks like this. It is a very strange graph. But you think about it, it had a squared term in it, which makes it look kind of like a parabola. It also had a sine in it, which is going to make it wiggle. And you're like, okay, so graphically, down here the derivative is 0. That's not a problem. And I don't have any, sudden changes in the derivative, right, where the tangent line, there's no, corners or anything like that. And the steepest it gets is somewhere in here, and is that vertical? Not quite. So the graph agrees with, yeah, that should have a derivative at every point. Oh, there's that one. Sure, now it shows up. That's that graph that I was drawing earlier. I don't know what is going on with these. All right. So let's do this one. Find the tangent and normal to the ellipse. X squared minus xy plus y squared is equal to 7. When you did conic sections in Algebra 2, and I don't know, did you redo them in pre-cal? Did you look at circles and ellipses and hyperbolas and parabolas last year? Every time I ask you guys about last year, you all look very sheepish. All right. So this is an ellipse, and the xy term, your ellipses were normally either, long ways horizontally or long ways vertically. What happens when you have this xy term is it rotates it. Okay? So you can make more interesting looking things. So we're going to I'm going to write it out again this time, the derivative with respect to x of both sides, x squared minus xy plus y squared equals the derivative with respect to x of 7. So the derivative with respect to x of x squared, that's just 2x. Minus, now I have a product, x times y, so I have to use the product rule. X times the derivative of y with respect to x, which is dy dx. Plus y times the derivative of x with respect to x, which is just 1. Plus the derivative of y squared with respect to x. The variables don't match, so I'm going to use the chain rule. I'll have 2y times the derivative of the inside part, which was y, that's dy dx, is equal to 0. And I need to close my parentheses here. So now I need to isolate dy dx so that I can solve for its value. So let's see, I'm going to have a negative x dy dx and a positive 2y dy dx plus 2x plus y is equal to 0. I'm going to do two steps at once here. I'm going to factor out the dy dx out of the first two terms and subtract the last two terms over to the right side. So I'm going to have dy dx times negative x plus 2y is equal to negative 2x minus y. Then dividing, we'll have dy dx is negative x minus y over negative x plus 2y. And a real quick, by the way, a lot of times you'll have something like this, and they'll rewrite it as 2x plus y over x minus 2y, so that there are fewer negatives. They just have multiplied top and bottom by negative 1. It doesn't really matter for this problem. I just wanted you to know that because that comes up on multiple choice questions. So then the slope is going to be negative 2 times 2. I'm sorry, negative 2 times negative 1, because the x value is negative 1, minus the y value, which is 2, over negative x, so that's going to be 1 plus 2 times y so that's 2 minus 2 over 5. That doesn't seem right. Fact is, I'm pretty sure it's not. No, what did I do wrong? You guys look too. Help me out. Ah, there it is. This should be a minus y. So this is going to be plus. And then this would be minus. So the slope of your tangent is 4/5. So for the tangent, we have y is equal to 2 plus 4/5 times x minus -1, which will be x plus 1. And then for the normal, to have y is equal to 2 minus 5/4 times x plus 1. And the graph looks sort of like this. Here's your rotated ellipse. You've got your tangent line here, and then your normal line here. All right.